n is 4 would be like 1 plus 2 plus 3 plus 4. Here's solution number 1. So we're going to use a nested for loop. And the way that it works is that if n is 4, on the very last loop, we would do the inner loop 5 times, because we can see that I is I plus 1, so it goes up to 5. So this is an okay solution. Solution number 2, we just use one for loop, so it just goes up to 4, and we just do this 4 times. And solution number 3 would be just to run one line of code, and then it would immediately give you the answer. So the best solution is the shortest one, and the worst one is the first one. And the way that we want to think about this is how much work does the computer have to do if n gets bigger? So I think humans like to think in linear terms. So you might say, okay, well, solution 1's bad, and if we put in n equals 4, maybe it'll take 3 seconds. So what happens if we do like n equals 8? We just double the size of input. Maybe it would be 6 seconds. We just double the amount of time. But the growth rate for these 3 solutions are vastly different. So this topic of time complexity, it describes the amount of quote-unquote time it takes to run an algorithm. But we don't want to think about it in terms of sheer time, because some computers are slow and some computers are fast. So if we have a very slow solution and we put it on a supercomputer, the time it would take would be very quick. So it's not a fair comparison. So the way we want to judge how good algorithms are is by counting the number of operations the algorithm needs to take to actually get to the solution. That's the fairest way. We use this to compare the efficiency of different algorithms and see how this changes as the input size grows. So the first one is quadratic. It's O of n squared. And solution 2 is linear, O of n. And solution 3 is the best. It's a sparkle. It's O of 1. So this is kind of like a primer to how we want to think about this. This is a graph that shows growth rates for different kinds of time complexities. Generally, linear, logarithmic, and constant are considered very good, and quadratic and exponential are considered bad. But for the purposes of our talk, the way you want to think about this is quadratic is also kind of good. Exponential is the worst. So a great way to just think about this is, safe. So as the input size grows, the time it would take also grows, right? So if we look at like the yellow line, if we're here, if the input is like very short, then the time is like very short as well. But then if we grow the time, of course, like the time grows, right? So if we like compare the time just up to here, they're all kind of like around the same area. But then if we just kind of go here, it's kind of like a tripling of the input size. Everything is pretty okay. But if you consider exponential, like try to imagine where the pink line would be if we were here. It'd be like in the sky somewhere, right? So it grows very, very rapidly. So exponential is like terrible. It's the worst. So they use these fancy terms, P and P, but really P problems, the way we want to think about this is certain problems are verified very easily, and certain problems are also solved very easily. So let's say we had like a tic-tac-toe board, and we wanted to verify that the winner had like 3 things in a row. It'd be very easy to do. And also the computer would be able to kind of play tic-tac-toe and solve the tic-tac-toe board very easily. But NP problems are slightly different. You can verify certain things very quickly, but solving the actual algorithm or the game is actually incredibly hard. So NP is the set of all the problems that exhibit this behavior. So some of those games or examples would be like chess. That's why they need like Watson, a supercomputer, to kind of play people. AlphaGo would be like an NP problem, and also surprisingly Sudoku. Sudoku is an NP problem. It seems pretty simple to us, but it's pretty hard for the computer. So yeah, it's considered an NP problem. It's easily verifiable, so if you solve it and kind of feed the numbers into the computer is smart enough to go, okay, every row needs to have numbers 1 through 9. Every I don't know what you call it, a quadrant. It's not really a quadrant, but every 3 by 3 matrix needs to also have numbers 1 through 9. So it's very easy to verify for a computer. But if you give it some numbers and empty spaces, it's very, very hard for the computer to solve. So the time complexity here is n to the n. So n is the possibilities for each square. That would be 10, 9, 1 to 9. And then n would be however many blank spaces you give it. And to kind of show you why this kind of grows at such a fast rate, I'm going to hand over.
So Sudoku is already an easy problem to visualize and conceptualize as humans because most of us either play it or know somebody who played it. So we're going to take, for example, a 4x4 Sudoku board. And this one over here has 1, 2, 3, 4, 5, 6, 7, 8 empty slots, right? So considering the algorithm that we saw on the previous slide, this is going to take 65,000 operations to execute. Now considering like you're running your normal computer, which has like a 1.8 gigahertz CPU, okay, it runs like 1,800,000,000 operations a second, right? So like the amount to solve this is going to be probably less than a second, right? Like can I have a show of hands who thinks it's going to take less than a second? Okay, great. It takes less than thousandths of a second, right? But that's with a 4x4 grid. So let's go to a 9x9 grid. This one has approximately like 32 empty slots, and okay, 56, excuse me. And it's going to take that many operations. So it's 2.73 to 10 to the power 53. Okay. So considering the same CPU, and we find that it would take like that amount of years to solve, not operations, not seconds. That's like amount of years. Does anybody know how long the universe has existed for? Anyone? 12 billion. Okay, 12 billion is 12 zeros. This is 36 zeros. Okay, so it's like crazy. It's only a Sudoku. Like, you think like Sudoku is freaking easy to solve, right? It's fucking horrible for a computer. So anyway, so like this concept, this idea of these P versus NP problems is so important that there's like, there's Clay, the Clay Institute of Mathematics, which is like in New Hampshire, I think it's like in the state right above New York. And it awards like $1 million for whoever solves one of those problems. And the P versus NP problem is one of those problems. Okay? So like one might think like, okay, so what? Like P equals NP or P is not equals to NP. Like, yeah, okay, great. So what happens if P is actually different than NP? Like these problems are not in the same category as these other problems. So nothing will happen. Okay? Because this is how we're operating right now. Like every time we try to encounter a problem and we design a library to solve it, this is how we've been running for like the last 100 years. Okay, so like this has been such an important topic that like people like scientists get bold and stuff. And in 2002, like 61% of these guys, they said that P is different than NP. And in 2011, 83 were like, okay, like P is certainly different than NP. And this is not in the slides, but like 5% were like, we don't care. Okay, so, but like to see how this would affect us as humans, right? Because I don't know who cares other than like if it would really affect humanity. So we're going to take the traveling salesman example. I'm sure the data science people know about this. Web dev guys, the traveling salesman is just, oops, this is very wrong in order, but it's okay. Okay, so the traveling salesman problem is like given the list of cities, what is the shortest way to hit every one of it and come back to the original city in the fastest time? Okay, so the traveling salesman problem is an NP problem. So it's very hard to solve, but it's very easy to verify by computer. Right? So like a very good example of this in real life would be, for example, the shipping of merchandise. right? Like we have this container ship that it needs to leave like the port from Amsterdam. It wants to hit like somewhere in France, somewhere in Africa, go to Lebanon, hit Greece, and get back to wherever it's going. So let's say like this can be solved quickly, right? That would mean that like the whole transport system would be affected, and that means that like gas emissions go down, like commerce is drastically changed, which means economies are drastically changed, and which also means that each and every one of our lives is also affected, because like instead of paying $5 for a burger, because the meat comes from Brazil, we're paying like $50 or something like that. So other than like the traveling salesman and like transportation issues, encryption like would become impossible. I don't really know why, but like, it's something in the way algorithms have to be solved. Also, we would have almost perfect real-time image recognition. We would have drastically improved language comprehension and translation, and also enhanced the modeling of weather, earthquakes, and natural phenomena. So if you have the solution, please send it to us, and we will share the price. It's even we have like I think it's
Woo!
and that's it. Question? Yes, in the back.
So it's on your slides that the solution is verifiable but not solvable. So what does it mean that it's verifiable?
So verifiable just means to see if the solution is correct. So if you think about Sudoku, the rules of Sudoku are that you need numbers 1 through 9 in every row and every column.
Yep.
And if you look at the upper left quadrant of a 3x3 matrix, you also need in that matrix the numbers 1 through 9.
Yep.
So if you solve the Sudoku board and feed the solution to the computer can just go through each row, go through each column, go through each quadrant, and check to see that it's correct. And it can do that very quickly. That's what we mean by verifiable.
Okay.
Yes?
Can you use machine learning to tackle NP problems?
Yes. So I think that's exhibited in like AlphaGo and like Watson. They use deep neural networks, multiple computers like communicating to each other all at once to come up with solutions in a reasonable amount of time. So yes, Sudoku. When we went over Sudoku, we kind of rigged it. Like that's one of the worst solutions to Sudoku, but it's kind of reasonable. People have come up with better solutions to Sudoku where it can be solved in a more reasonable amount of time.
So would the implication of P equals NP be just that like we've been going at this whole computing thing wrong? Is that like the idea?
So
Maybe you can show me the first step.
I think the way to think about it is they exhibit similar behaviors on certain characteristics, and they're related to each other. So they're like a set of each other. So if somebody comes up with a solution and proves that P equals NP, then we would know that they're really the same thing. So we could apply a certain kind of strategy that we use to solve P problems to NP problems as well. But nobody's been able to prove that.
Remind me, the solutions to NP problems are unverifiable? Is that right?
They're quickly verified, but solving them is very slow.
Okay. And well, my question was, if it's unverifiable, how's it a solution? If it's that. Can we go to the slide that goes over that?
It's the heavy fall of the first
Okay, actually. All right, never mind.
Okay.
Never mind.
Thank you.